Okay, so let's give ourselves some boundary conditions. When y equals 2, x equals 0 and the differential is 0. So we've got those boundary conditions, put them into our general equation. We're going to hit a problem when we come to the differential because we've got two functions multiplied together involve x, so we're going to need to use the product rule for that bit. But let's go ahead. So the first one's not so bad. Let y equal 2 when x equals 0. Then we can write the general equation as 2 equals, if x equals 0, then a times 0 is 0, so we're just left with b times e to the 0. So that's a bit more like it, isn't it? Anything to the power 0 is 1, so b equals 2. So we've got b. So we're in a situation where we haven't got a simultaneous equation to worry about. We've worked out what b is. Now we need to find a, so we're going to use our second condition for that. So now we need to take this function y equals ax plus b e to the minus x and differentiate it using the product rule. So I have to let this bit equal u and this bit equal v, if you remember, the two separate functions. So I split my page into two. On the left hand side, what's u? Ax plus b. On the right hand side, what's v? E to the minus x. And then we differentiate them. A. Because the b disappears, it's a constant, and the x disappears. And the v by dx minus e to the minus x, because the minus 1 comes down and goes in front. So the product rule is u dv by dx plus v du by dx. And again, you've got this formula in your formula sheet, but remember it. It just is the first bit multiplied by the differential of the second plus the second bit multiplied by the differential of the first, if you remember. So it's going to just equal u, which is ax plus b, times dv by dx, which is minus e to the minus x, plus v, which is e to the minus x, times the differential of u, which is a. So that's our differential. It might look horrendous, this, but when we put our boundary conditions in, remember now, what have we got? When x equals 0, the differential is 0. When x equals 0, the differential is 0. And when we put these boundary conditions in, it all becomes a lot more straightforward. 0, the differential is 0. Anything to the e to the power 0 is always 0, so if x is 0, we get the first term. A, if x is 0, the a goes, so we're just left with b times minus 1, because anything to the power 0 is 1, plus e to the minus x is 1, so that's just a, and we get this. Now we know what b is. We know that b is 2, so we can find a. So therefore 0 equals minus 2 plus a. So a must equal 2. So we've got a equals 2 and b equals 2. So we can now write down our particular solution. Y equals 2 e to the minus, ax plus b, so that's 2x plus 2 e to the minus x is our particular solution. So that's our particular solution, and if we just look at it on autograph, it looks like this. And like lots of these things, this will be time along here. So we're only really going to be interested in what happens in the positive quadrant here. We're not interested in what happens on the left. But there it is. And actually thinking about what we're doing in Laplace, it's designed so that it's meaningless to the left here. It only makes sense for positive values for x. But here it is. And if we looked at our particular example, we set some boundary conditions, and we set the boundary conditions that when x equals 0, y equals 2, and the differential was 0. So the gradient should be 0, which it is, and it's cutting at 2. And this is actually a situation, if we try and apply it to our model that we looked at the beginning of today, this is a perfect damping situation. There's no overlay, there's no sort of swinging the other side, no oscillation, it's just dropping straight down to 0. So in a damped situation in the car, that would be almost the ideal, wouldn't it? Okay. So that solution is often what we're looking for, a perfect square solution where we've just got one result. Okay.